In this podcast episode, Dr. Janna Levin, a distinguished astrophysicist and professor at Barnard College, unravels the cosmic tapestry that leads from the Big Bang to the possibility of life beyond Earth. She begins by addressing a common misconception. The Big Bang was not an explosion within space, but rather the simultaneous bursting forth of space itself from an initial singularity. This event marked not only the origin of matter and energy, but also the birth of space and time, reshaping how we comprehend the beginning of everything. Levin invites listeners to reimagine the Big Bang, not as a localized blast with a center, but as an expansion occurring everywhere, so that every observer, regardless of their position in the universe, perceives themselves at the center. This perspective is a profound shift in understanding, rooted deeply in Einstein's theory of general relativity and supported by Edwin Hubble's astronomical observations during the early 20th century. The universe, as revealed through decades of science, is not static but expanding, with galaxies receding from one another as space stretches. Levin explains that the Big Bang is more accurately pictured as space itself expanding, akin to the surface of a balloon inflating, where every point moves away from every other point. Importantly, time itself began at this event. Asking what came before it is a question rendered meaningless by the nature of time's origin. The hot, dense state following the Big Bang produced a universe teeming with elementary particles, simple elements like hydrogen and helium, and a bath of energy and light still observable through cosmic microwave background radiation. What makes this explanation so fascinating is how well it fits with predictive models that have been tested and refined over decades. The aftermath of the Big Bang not only accounted for the abundance of primordial elements, but also created the initial conditions for all cosmic structures to form. This radiant afterglow, cooling over billions of years, gives us a direct observational window into the universe's infancy, validating the Big Bang as our best scientific explanation for the origin of everything. A critical part of the universe's story involves stars acting as cosmic furnaces that transmute primordial hydrogen and helium into heavier elements essential for planets and life. Dr. Levin highlights how the cores of stars serve as sites of thermonuclear fusion, where intense pressure and heat enable the forging of carbon, oxygen, nitrogen, and beyond. These heavier elements are essential building blocks for rocky planets and ultimately for life as we know it. However, these elements do not become available for planetary formation until stars exhaust their fuel and undergo supernova explosions. Such cataclysmic events eject enriched material into surrounding space, seeding future generations of stars and planets. Thus, the very fabric that makes up our planet and ourselves is literally stardust, remnants of ancient stars that have lived and died, enriching the cosmos with the ingredients necessary for complexity and life. Levin paints the formation of planets as a byproduct of these stellar cycles. As clouds of gas and heavier elements, produced in stars, cool and collapse under gravity, they coalesce into protoplanetary disks. Within these disks, material accumulates into distinct bodies, resulting in the diverse array of planets we observe. The arrangement and composition of planets depend on their distance from their star. Rocky planets form close to the star where it is hotter, while gas giants emerge farther out, rich in lighter elements. Regarding our own solar system, Levin emphasizes Earth's uniqueness, especially its magnetic field, atmosphere, and plate tectonics, that together create a delicate balance allowing liquid water and the emergence of life. Our moon, too, born likely from a colossal early collision, plays a vital role in stabilizing Earth's rotation and influencing cycles crucial to life. The array of moons orbiting giant planets presents additional intriguing locations where life might exist under subsurface oceans, expanding the scope of habitable real estate beyond traditional planets. The search for life extends beyond planets to their moons, especially in our solar system, where bodies like Jupiter's Europa or Saturn's Enceladus have subsurface oceans hidden beneath ice crusts. These environments are of great interest because they could harbor microbial life, possibly similar in form to some extremophiles on Earth. Levin underscores this focus on moons as a window into extraterrestrial biology, as these bodies might offer more stable or persistent habitable conditions compared to many planets. She also stresses that if life exists elsewhere, it may differ radically from our carbon-based, oxygen-breathing, water-dependent norms. Life on other worlds might utilize different biochemistries or sensory mechanisms, bound by their own unique evolutionary pressures. Hence, astrobiology demands openness to unfamiliar forms of existence, possibly detecting life forms that do not conform to human preconceptions of intelligence or biological function. Dr. Levin approaches the perennial question of extraterrestrial intelligence with a cautious yet optimistic stance. While we cannot yet definitively prove the existence of intelligent life beyond Earth, the sheer vastness of the galaxy and the ubiquity of planets strongly suggest life elsewhere is plausible. The Milky Way alone hosts hundreds of billions of stars, most accompanied by multiple planets, creating countless opportunities for life to develop. She discusses the Fermi Paradox, the conundrum of why, despite the vast number of possibilities, we have no confirmed contact with alien civilizations. Levin acknowledges the possibility that technological civilizations may self-destruct, or choose paths making them undetectable. Alternatively, they might evolve in ways fundamentally different from human expectations, or the vast distances and limits of physics might decouple us from contact. Yet, she resists nihilistic conclusions, highlighting ongoing efforts and renewed enthusiasm in astrobiology, fueled by new exoplanet discoveries. Dr. Levin provides a compelling narrative on the nature and genesis of black holes, explaining them as inevitable collapse end states for massive stars. Early theoretical work by physicists such as Carl Schwarzschild and Roger Penrose established that once stars exhaust nuclear fuel, their cores can collapse under gravity to form singularities, objects so dense that space and time are violently warped, creating event horizons beyond which nothing, not even light, can escape. This revolutionary idea challenged early skepticism, including from Einstein himself, who doubted the physical reality of black holes. However, over the decades, the accumulation of theoretical rigor and observational evidence transformed black holes from mathematical curiosities to vital astrophysical phenomena, essential to understanding stellar life cycles and cosmic evolution. Levin reframes black holes not merely as cosmic vacuum cleaners, but as extraordinary regions where space and time themselves are distorted. She likens them to places, defined by intense warps in space-time geometry, rather than destructive forces reaching out indiscriminately. Objects can stably orbit black holes at close range, with those orbits differing qualitatively from orbits around normal stars due to relativistic effects. One of the most fascinating phenomena near black holes is gravitational time dilation, whereby time appears to slow down measurably at the event horizon compared to distant observers. Levin illustrates how this effect can be conceptualized by imagining a falling astronaut whose experience of time differs dramatically from a stationary observer watching from afar, an effect portrayed in popular culture such as the film Interstellar. The singularities inside black holes remain a frontier of understanding, where classical physics breaks down and quantum gravity effects perhaps emerge. The detection and study of black holes have advanced remarkably, from early X-ray observations of X-ray binaries, where black holes consume companion stars, to the recent photographic capture of the silhouette of a supermassive black hole's event horizon via the Event Horizon Telescope. Levin shares personal connections to pivotal projects and discoveries, conveying the excitement of direct observation that confirms decades of theory. These observations reveal black holes as engines of powerful jets and phenomena shaping their host galaxies profoundly. For instance, the supermassive black hole at the center of the Milky Way, Sagittarius A, has been studied through the orbits of nearby stars, demonstrating its overwhelming mass concentrated in a very compact region. The photograph of M87's black hole shadow, characterized by a glowing ring of hot plasma, stands as a monumental scientific landmark. Beyond astrophysics, Levin touches on humanity's evolving relationship with technology and consciousness, reflecting on how rapid technological advances challenge our evolutionary capacities and social behaviors. She considers the role of AI, distinguishing between powerful computational abilities and genuine consciousness or experience, a nuanced position that underscores the complexities of intelligence and awareness. Moreover, she muses about the potential biological and cultural shifts in human evolution, shaped by our dependence on technology from fire to smartphones. Just as stars transform matter and black holes distort time, human beings are caught in processes that simultaneously empower and threaten their survival. The notion of future isotopian societies, those which reconcile technology and nature, contrasts with dystopian trajectories, emphasizing the pivotal crossroads at which we stand. Levin's fascination with the fundamental fabric of reality shines through in her reflections on theoretical physics explorations, including theories involving extraspatial dimensions beyond our perceptible three. She describes efforts to understand the universe via topological spaces and how such high-dimensional frameworks might leave subtle imprints on observable phenomena, such as the handedness, chirality, of fundamental particles and cosmic background radiation patterns. These efforts illustrate the quest to discover a theory of everything that unifies quantum mechanics, gravity, and cosmology. Black holes serve as critical test cases in this endeavor, acting as natural laboratories where the limits of known physics are probed and new principles may emerge, bridging our understanding from the cosmic scale to the subatomic.